Hey everybody, welcome to the guided assignment for chapter 14. I'm going to there's only 3 questions, but it will take a little while because some of these things are a little complicated. But what I'm going to do is I'm going to try to show you both the way to work some of these out by hand. I mean, we're still going to use Excel, but we're not going to use Excel functions, but then also show you how to use Excel functions or Excel tools to go ahead and work out some of these. So here we are on the first one. They give us 5 observations for 2 variables, X and Y. So I'm just going to go ahead and enter this in. And I found that Excel works a lot better if I do my variables vertically. So my X variable is 1, my Y variable is 3, 2 and 7, 3 and 5, 4 and 11, 5 and 14. So when we're working with um, when we're working with like a straight linear regression like this, and simple linear regression, it means we have 2 variables and they're related to each other. Okay, and related in the sense that X is an independent variable and Y is a dependent variable. So what we're saying is that we believe that a given value of X leads to a given value of Y. Okay, or at least an expected given value of Y. And what we're trying to do is establish or understand the nature of the relationship between these 2 variables. We call a set like this 1, 3 or 2, 7 or 3, 5 an ordered pair. You probably learned about this some point in high school math, or in some cases even middle school math, but you forget a lot of stuff when you don't use it. So we have 5 ordered sets, okay, in this data set. And so if we want to know what the n was, the number of numbers, it's not the total number of numbers, it's the number of ordered pairs. So we have an n of 5. All right. Anyway, so the first question it wants is for us to um, answer which of these following scatter diagrams accurately represents the data. So even if we didn't draw it out or anything, we could just see that it seems like when X goes up, in this case, Y goes up, and then X goes up more, Y goes up more. Here we see when X goes up another one, there's a little drop to Y, and then X goes up, Y goes up, X goes up, Y goes up. So we would expect some type of a positive linear relationship. Um, and so this shows a negative linear relationship where the numbers are sloping down. Here, they're kind of all over. And here we see an overall positive, but on this one, it drops a little. So probably without even graphing this, we could just look at it and be like, okay, number 3 is the correct diagram. But if we want to, we can have Excel do the work for us just by highlighting our data set this way. It always assumes X is on the left and Y is on the right. And then we can insert and come over here to charts, and you see how there's all these different there's one that looks like a bar chart, one that looks like a pie chart. This one that has all the dots in there is a scatter chart. So if I hit the drop down, click the scatter, you can see it'll just plot it out for me. And that does indeed look very much like number 3. So there's our first one. All right. It says, B, what does the scatter diagram indicate about the relationship between the 2 variables? And so I would say it looks like they are positively correlated. And so what is that? Choices, it says positive or negative. And again, positive just means that as X goes up, Y goes up, okay? Negative would mean that as X goes up, Y goes down. All right, part C, try to approximate the relationship between X and Y by drawing a straight line through the data. So again, we can draw a line kind of through there and see that number 1 here is clearly the correct one. But if we wanted to, instead of having to approximate it, we can come in here on Excel, and this little plus button right here lets us add chart elements. And one of the things we can add is a trend line. And now we can see that that trend line looks pretty much exactly like the one here in Excel. We can edit it if we want to. If you right click on that, you can edit that line so it's not dotted, so it's solid, whatever you want, but I don't think it's necessary for the task we're doing right now. So I'm going to say number 1 is the line that most closely approximates this scatter plot here. All right. Part D, develop the estimated regression equation by computing values b sub 0 and b sub 1 using equation 14.6 and equation 14.7. Okay, so I'm going to show you the hard way to do this, and then I'm going to show you the easy way. But I think it's that sometimes seeing the hard way helps us better understand what the data is. In other words, what is the equation for this line? Again, probably in high school or even junior high math, you learned how to figure out the equation of a straight line. We always learn them as y equals mx plus b, where m, uh, where m was the slope of the line, meaning for each amount x goes over, how much does y go up, and then the number by the x, we called that the y-intercept, and it was where this line would cross y, right? But here they do it backward in statistics, where they don't represent this as m and x, they represent this as b sub 0 and then b sub 1. Okay, so it's a little confusing. And hopefully I didn't just say those backwards to make it more confusing. So if we click here, it'll show us this formula, and that formula looks pretty intimidating, but I'll show you how we can calculate b sub 1. All right, so b1, and I'm not gonna bother putting this as a subscript. It's more work than it's worth, so I'm just gonna call it b1. And you can see that it is the sum of xi minus x bar times y I minus y bar. Okay, that's a little confusing to begin with. If you remember, x bar just means the mean of the x values. Okay, so I'm going to do equals average, and then I'm going to just highlight all of the x's, and that gives me x bar. I can also find y bar the same way, equals average, and then we'll just highlight all the values of y. There's our x bar and our y bar. And so now, if I want to figure out what xi minus x bar is, I would just say this equals the value of x. Xi means x for a given example of x, okay, minus x bar. And I'm going to lock in this average or mean. That way, when I use my fill tool, it stays, you can see it's doing A4 minus the mean, A3 minus the mean, A2, A3, A4, A5, A6, etc. So there is my value of xi minus x bar. Okay, I'm going to do the same thing for yi minus y bar, where I take the value of y minus the mean. And the same thing where I lock in that mean. So I know the numerator of this is going to be the sum of xi minus x bar times yi minus y bar. So I'm just going to say column C times column D. That's what I'm going to do here. So column C times column D. And then if I take the sum of those, there's my numerator, 26. One more thing I have to do is, you can see that the denominator of this is the sum of xi minus x bar squared. So I have xi minus x bar. So if I do xi minus x bar squared, so I'm just going to take the value of C2 and square it. And now if I take the total of that, or the sum of that, that'll give me my denominator. So B1 is going to be my numerator divided by my denominator, or 2.6. So the slope of this line is 2.6, okay? That's what all that work was to figure out, that each time the line goes over 1, it goes up 2.6. Over 1, up 2.6. There's the slope. Now, to find the y-intercept, we just take y bar. Here's our formula again. Y bar minus B1, which we just figured out, times x bar. Now I'm going to go ahead and put the B sub 1 times x bar in parentheses, and I'm going to get a y-intercept of 0.2. So we're saying this line is going to cross at 0.2. Okay, so I would put that this is, let's see, oh, and then I was going to show you the easy way to do it too. So that was the hard way, right, to find out these values. I can also, once I've done my chart here like this, if I just right click on the line that I made, the trend line, and click Format Trend Line, I have an option to display the equation on the chart. And once I do that, it just shows up right there. And you can see it shows as y equals 2.6x plus 0.2. We're going to put it in here as 0.2 and 2.6x. That's just how they write it in stats. So that was not too bad. This is a little bit complicated, right? But we can do it. We just have to find out the x minus xi minus x bar, the y minus y bar, multiply them together, take the total, then square the x minus x bar, and then divide it. And then, so I mean, there's a little bit of work, but it's still doable, but way easier to just say, hey, Excel, tell me what the equation of this line is. And then the last question here is to use the estimated regression equation. So that's this equation we just figured out to predict the value of y when x equals 4. So if I put x is equal to 4, then y, they call it y hat, which actually means like the estimated value of y, okay, for a given value of x. And then we just put in this formula, 0.2 plus 2.6 times the value of x. So 0.2 plus, actually, I'll go ahead and use my numbers I've created, plus 0.26 times our value of x. All right, so if we get an x of 4, we would expect y hat, or expect y to be 10.6. Now we have a nice working calculator, right? We can change any of these variables, and that will change for us. All right, so that's the end of the first question. Hopefully that wasn't too bad. And hopefully you learned some tools in Excel that will be helpful to you as we move forward into the next problems and maybe in some real life applications you may be facing. Okay, so let's move on to number 2. And I set these up so they use the same numbers in all of them. So you can see we still have the 5 observations, and they're the same as the ones we had before. And then it wants us to, it gives us the regression equation, which is the same one we figured out before, 0.2 plus 2.6x. And now it wants us to compute the sum of squares error, and the sum of squares total, and the sum of squares, oh, what is the R? I forgot what the R stands for. Regression, sorry. So again, they were nice enough to give us the formulas here. So if we want to do it with the formula, we totally can. So I'm going to actually do the first one using the formula, and then you'll see how you could do any of these with the formula. But also, I'll show you how to use the regression tool, which will do a lot of the hard work for us. All right, so let's just find our sum of squares error. And so you can see that our sum of squares error is a given value of y minus the estimated or expected value of y. And so what that means is for each one of these given values or not given values, but this would be an observed value of y, right? This is what we actually observed, that when x was 1, y was 3. When x was 2, y was 7, etc. But we've come up with this little formula, y equals 0.2 plus 2.6x. So that's going to tell us, I'm actually going to just hide these for a second because I think they're in our way a little bit. So I'm going to call this one y hat, okay? And we're going to say, hey, what would I expect to see y as if x was 1? And again, I could do this using the formula equals 0.2 plus 2.6 times x, right? And I could put in using these, whatever, I just typed them in this time. So what we're saying is, according to our little regression formula here, we would expect that if x was y, that y would be 2.8. What we actually observed in this case was that y was 3. So it was a little off from what we expected. And we can use that formula all the way down, and we can see that some of them are closer. 10.6 is pretty close to 11. Some are a little farther away than what we'd expect to see. And so now we have the observed value of y and the expected or estimated value of y. So to find the sum of squares error, if you think about that, by error, and in Excel they call this the residual, but they mean the same thing. It just means the difference between what we would expect to see and what we actually saw. Okay, so this is going to be yi minus y hat. So the difference between what we actually saw or observed and what we would expect it to be. Then to find the error, what they call the error, okay, we're going to take this number, the difference between what we expected or what we actually saw, what we expected to see, and we're going to square it. And finally, we'll take the sum of the squares. So that's what we call this, the sum of squares for the error, or in Excel, when I'll show you when we use the regression tool, it calls it the sum of squares residual, so 12.4. Okay, and we could go ahead and work the same thing. You'll see that the sum of squares, I'm going to skip total and go to regression here, is just going to be the y hat, so what we expected to see minus the average squared. And then the sum of squared totals is going to be the observed value of y minus the average, or the total difference, okay? But instead of working each of those out that way, I'm now going to show you a tool. You may or may not have this set up in Excel, so I'm going to show you how to set it up. So when we go to data or data, depending on how you like to say it, there's all these different categories: get and transform data, queries and connections, sort and filter, etc. And way over here is one called analysis. And this data analysis tool will help us really do this. If this isn't set up in your Excel, you can set it up by going to File and then Options. And some people said they don't have options, and mine had more on the other version I had of Excel, and then you went more and then Options. But so you go File, then Options, and that gets you to the Excel options window. You go to Add-ins, hit OK. Oh, actually, you don't have to hit OK, because that'll sorry about that. Go to File, Options, Add-ins, scroll down, and down at the bottom it says Manage Excel Add-ins. And if it's not on add-ins, you can choose it from this list, but mine's already on it. Hit Go, and then we just click the Analysis tool pack right here. click, like mine's already clicked, so I'm good. And hit OK. And then when you go back and hit data, that'll be there for you. Okay, so that's how you set it up. All right. So if I want to run a data analysis now, okay, I'm going to click data analysis and I'm going to tell it what type of data analysis I want to run. And right now we're going to do what's called a regression analysis. We'll hit OK. Then we have to tell Excel some things. We have to tell it, number one, what is our Y range, which is going to be all these values of Y. And number two, what is our X range? You have to be careful when you do it because it will often assume like that the X is on the left and Y is on the right, or it'll assume it. Actually, it will assume it backward. For some reason, it has Y then X first, but in other things it doesn't. So you have to look at it carefully and just click here, highlight all your Y's, click here, highlight all your X's. Then you have to tell Excel, hey, I want you to output this report, this regression analysis report somewhere. And you can have Excel either do it on this worksheet by telling it where, like you can just click on that and then just click on a cell. And now I'm telling it, put this on, put this on K3. And that'll be the upper left-hand corner of my report. You can also tell it to put it in a new worksheet. So it'll just create a new sheet or a new workbook, which will create a completely new Excel workbook. I'm going to tell it to put it in K3 for now. Hit OK, and you'll see it will pop up. Whoops. I'm just going to move my chart out of the way for a minute so I can show you this. So this is the summary output from a regression analysis. And it comes up with some pretty cool stuff. It gives us, let's see if I can show you some of the stuff we just calculated. Like our sum of squares error. Remember, I told you it calls it sum of squares residual, meaning it's the difference between what we actually observed and what we expected or estimated we would observe. It also gives us our sum of squares regression, which is called SSR, which again, we could have calculated, and it gives us our sum of square totals, which we could have calculated. It also gives us, it calls these the coefficients, which is the x-intercept and the slope. So you have to kind of know what you're looking for here, but it gives us all that information. And then there's some other stuff that you'll see that we'll use in a minute that it also gave us. So it gives us a lot. So I can now go back and look at my SS, or sum of squares. I see that my SS, what it calls SSE, is called residual, sum of squares residual in Excel. So the sum of squares total, 80. And the sum of squares regression, right here, 67.6. I think it's beyond the scope of our worrying about it for this course. But whoops, did I put 12.4? Yeah, that's right. Just recognize that this is kind of telling us how much of our I don't want to use the word variance, but the difference between what we expected to see and what we actually did see, how much of it comes from error, which is what we expect and what we did see, and how much of it comes from just the regression, which is what we expected to see minus the mean, and then how much is the total. Okay, so it's just really what we're trying to see is how much of our differences that are occurring here are based on error and not something else. And so that's what we're really seeing. And that's as much as we really need to know about this for this stage. If you go on to study more statistics, of course, you would learn more about it. All right, so then it wants us to compute the coefficient of determination. And the coefficient of determination, we can calculate with a formula, which, let's see, is a formula I do not have memorized, but it is, let me just tell you, for your information, I'm looking in the book. because I don't use this ever in real life. All right, I'm almost there. All right. So the coefficient of determination, sometimes called your R squared, okay? So we're going to call this R squared. We can just calculate that, dividing our SSR. So I'll move this over a little bit. SSR by our SST. In other words, we're saying what percentage of our sum of squares differences are to due to regression. And we'll see it's 0.845. Also, in our summary output, it's right here. So we didn't actually have to do this calculation because when we do our regression analysis, it gives you that as the R square. And then it asks, does the least squares line provide a good fit? And the answer is yes, because this number is relatively high, meaning closer to 1, okay? And then it wants us to do the correlation coefficient. Sometimes the correlation coefficient is just called the R. So we can calculate it by taking the square root of the R squared. Makes sense, right? Or square root of the R squared, 0.9124. And you can see that's also reported to us in our regression output as the multiple R. Okay. So again, we didn't actually have to do these calculations. We could have run this one thing and it would have given us all of these answers. But I wanted to show you how to do it. So to 4 decimals, that is 0.9192. We'll go ahead and check our work, make sure I didn't make any errors. And it looks like we are all good. All right, let's move on to number 3. All right, number 3, again, we have the same numbers here, 5 observations, X and Y, have them all. It gives us a regression equation. Now it wants us to compute the mean square error, MSE, using the following equation. So again, I'll show you how to do it. MSE, mean square error. But then I'll show you where it comes in this regression output. So if we look at the equation, the mean square error is just the SSE, the sum of squares error, or what we call sum of squares residual, over n minus 2. Okay, so we could say this equals the sum of squares. Let's see if we can. I think I put this output just a little too far over. All right, so our sum of squares error, which is SS residual, divided by n minus 2. N is our number of observations. And it's minus 2. So my MSE is 4.133333. And you can see that that number pops up in here as the MS of the error. Okay, so MSE, MS, and then we call residual and error are synonymous terms for us in here. So we calculated that as 4.133, or we also found it as 4.133. Compute the standard error of the estimate using the following equation. So if we click on the equation, we can see that the standard error of the estimate, or S, is just the square root of the MSE. So equals SQRT of MSE. And that comes out as 2.03306. You'll also see that that shows up over here as the standard error in our regression output. So again, I'm showing you how to calculate them, but also showing you where they fall in here. You may need to make in your notes, what term, like MSE, and where you find it in the regression output so that you can find it in the future. All right. We have 2.033. All right, then it wants the estimated standard deviation, or B sub 1. So we can do this equation. The S of B sub 1 is S, which we just calculated, divided by the square root of the sum of X minus X bar squared. Shoo. So we actually figured that out earlier. It's one of those that I hid because it was kind of being a pain to see. So I'm going to unhide for a minute here. So we have our X minus X bar squared, and the sum of that is 10, right? So to find the SB1, which is the estimated standard deviation of this, we're going to say this equals standard error divided by the square root. I guess I didn't need two parentheses there, of 10. I could have got away with just one. And there it is. We'll also see that that shows up over here as the standard error for X, or for the variable 1 there, okay? So again, here's how you calculate it. Here's where it shows up in your regression output. And it wanted 3 decimals, so 0.643. All right. So we have all of these numbers, and you might be wondering why, and I would say don't worry too much, just work with them, and then they start to make more sense. So now they want us to do a t-test to test the following hypothesis at an alpha as 0.05. And the hypothesis is that we have a beta B1 is equal to 0, or that it is not equal to 0. And what we're really doing this for is to see if there is a good, you can see right here our choices, a significant relationship between X and Y, or not a significant relationship between X and Y. Okay, so to compute this test statistic, again, it's a formula, and a formula that nobody except for someone who does this memorizes, and even they don't, because the computer does it faster. But I'll show you how to calculate it in a minute here. And it's this B1. I'm going to call this the t-test statistic. So it's B1, which we figured out a long time ago, okay, divided by the SB1, which we just calculated here. And that gives us this test statistic. And lo and behold, if we look at our output, we can see that under the t-stat, lining up with the X variable, is that test statistic, 4.044. So there's our test statistic, 4.04. And now we're going to find the p-value of that test statistic. Oh, that's taking you back to other chapters. And remember, it's just t.dist.2t, where X is the value of this test statistic, and then it's n minus 2 degrees of freedom. So n in this case was 5, minus 2 is 3. I'll just type it, but it's n minus 2 degrees of freedom. And that gives me our p-value. So the p-value is 0.027. Oh, wait. My p-value is somewhere between 0.025 and 0.05. So since our p-value is less than our alpha, okay, then we're going to conclude that this thing does not equal 0, right? And therefore, there is a significant relationship between X and Y. We can also do an F test. All we're really going to do is use the outputs of the regression analysis for this, and we'll look at that p-value because it does all the work for us, all the heavy lifting. So again, you'll see regression, residual, and total on mine, and then in the book, or on the Excel output, and then in the book or in the problem, you'll see regression error. Just remember, residual and error are the same thing. All right. And so under degrees of freedom, we'll see them listed as DF here. So we'll do 1, 3, 4. Under SS for sum of squares, we'll see 67.6, 12.4, and 80. Under mean square, we'll see 67.6 and 4.133. Under F, we'll see 16. Oh, it doesn't want. Let's see the mean square to 3 decimals. Okay, F ratio to 2 decimals, 16.35. And then it shows p-value here and significance here, but that's still this number they want, 0.02. How many decimals do they want? 4. 7.2. All right. And then the same thing, we're comparing this p-value to our alpha. And if the p-value is lower, then we'll conclude that there is a significant relationship between X and Y. And that's it. So I hope this was helpful. I know it was a little long, but I hope it showed you some tools and tricks that might make you better with Excel and might help you get through the rest of the chapter. And I hope you have a great day.